this the lecture session on dynamic inventory problems under risk. As you are already aware of that we have mentioned that there are the two types of approaches for problem formulation and solution. The first one is the cost based approach, and the second one is the service level based approach. We have already discussed the cost level based approach, cost based approach, and now we are discussing the service level based approaches. Now, as we have already pointed out that service level based approach is applicable only when the cost estimates or cost estimates do not have much reliability. In other words, the cost based approach is not considered feasible. There could be many reasons for this one, and that's why many a time we opt for service level based approach. We have already defined what is a service level. If you recollect, there are the two possible the definitions and measures of service level. The first one is the service per order cycle, and the second one is the service per units demanded. Now, when we try to incorporate the service level concept in the determination of the parameters of a given inventory control system, usually we use the second measure of service level, that is service per units demanded. In the previous lecture sessions, we have already defined the service the level the measure, and you will and particularly this measure or the notations which you have used, these are applicable for the Q system of inventory control, and we have used certain notations like SL bar, sigma L, NR, FR, mu. So my suggestion is you first get an idea about all these say the measures or the parameters, and the first thing you need to know, that is for which time period you are required to say determine the safety stock. If it is a Q system of inventory control, obviously the during the lead time there is a possibility of stock out, and that's why the service level based approach or the modeling is done exclusively for the lead time period, and accordingly the problem is formulated. Whereas if you try to say the model the problem for say the P system of inventory control, you need to define all these terms for the time period, which consists of two parts. One is the order period or the order interval, and the second part is the lead time. Okay, so we'll be referring to, we'll be discussing the model formulation part with reference to a Q system inventory control, so that your the understanding is appropriate, and I am sure that if you have appropriate understanding of the entire approach, the same the approach with obvious the modifications you can use for the P systems of inventory control. Now, we consider three types of say the demand distributions, and for problem formulation and solution. The first one is the uniform distribution, and we will be referring to the continuous type. That means we will assume that the random variable is of continuous type. Then the next important the distribution we'll consider, that is the exponential distribution for the continuous random variable, and the third one is the normal distribution again for continuous random variable. Now let us first talk about the uniform distribution of demand. Now the first thing you must know, that is given a distribution, what is the expression for mean and what is the expression for the variance. Now here for this particular distribution, that means continuous type uniform distributions, you have the interval between S0 and S1, and for any value say the between S0 and S1, your probability that remains same. So this is the notation, that is the F, that means the probability density function. So obviously, we use this term SL bar, that means the mean demand during lead time. L stands for the lead time. So the mean demand during lead time, that is SL bar, is S0 plus S1 by 2. So this is notations. Now what is F? F is 1 minus S1 1 by S1 minus S0, 1 upon S1 minus S0. So similarly, you can calculate the variance of say the lead time demand, and it is integration 0 to infinity x square fx dx. This is the general formula, I am sure that you are aware of, minus the square of the mean. So here this is SL bar square. Okay. So now when you substitute the expression for SL bar, that is S0 plus S1 by 2, and here what you find, that Fx is F, that means 1 upon S1 by S0, and then the integration from S0 to S1, that is x square dx. So if you integrate this expression and you manipulate, ultimately the expression for the variance during say the lead time demand is S1 minus S0 square by 12. Okay, so we have started from say we have used the fundamental principles in computing or in determining or computing the mean and the standard deviation or variance. So so the standard deviation during lead time demand is 1 upon 2 root 3 S1 minus S0, and S1 minus S0 is nothing but 1 upon F. So it is 1 upon F 2 root 3, and hence F is equals to 1 upon 2 root 3 sigma L. So what is the expression for S1 in terms of SL bar and sigma L? That is SL bar plus root 3 sigma L for the continuous uniform distribution, and S0 is SL bar minus root 3 sigma L. Now these are all well known expressions for uniform for continuous uniform distribution. Now we have used this notation for the safety stock, that is capital B, and the safety stock is expressed in terms of the sigma L, that means the lead time lead time demand standard deviation, and it is expressed as T into sigma L, where T is the multiplying factor. So ultimately when you determine the safety stock is to be determined in terms of T into sigma L. If the value of sigma L is specified, you need to determine the value of T. Okay, so later on, while we form the total cost equation, so this point will be made very, very clear. So the safety stock, the notation is capital B, which is nothing but T into sigma L. Okay, T is the multiplying factor. Now in terms of NR, we define the service level. So with respect to say the continuous uniform distribution, you must be able to derive the expression for NR, that is the expected number of unit short. Now this expression is given by integration SL bar plus B to infinity. That means during the lead time, what you consider the average demand during lead time, that is SL bar, plus the safety stock, that is capital B. Now if the demand during the lead time is more than SL bar plus B, obviously there is a stock out. And what we are trying to measure, we are trying to measure the expected number of units short during lead time, because it is a Q system of inventory control. So X is the random variable, X minus SL bar plus B, and corresponding probability density function is Fx dx. So now this Fx is 1 upon 2 root 3 sigma L. Already we have derived this expression. So integration SL bar plus B to S1. Okay. So that is the maximum value, X minus SL bar plus B to Fx dx. Is it all right? Next is, so obviously you go for the integration, and this is the lower limit of integration, this is the upper limit of integration. So this one is SL bar plus T into sigma L. T into sigma L is beta, and the maximum value, that is S1. So SL bar plus root 3 into sigma L. Already we have shown this the relationship between say S1 and SL bar and sigma L. So the next step, we get 1 upon 4 root 3 sigma L, root 3 minus T square sigma L square, and this becomes root 3 minus T square by 4 root 3 into sigma L on simplification. So hence service level is 1 minus mu into NR by sigma L. So the expression for NR is known, and when you substitute this value of NR in this equation, so what we get an expression for the service level when the demand is uniform. So this expression is 1 minus mu into root 3 minus T square by 4 root 3. Okay. Now the second, in the first case, when the demand distribution is uniform, so we derive the expression for NR, that means expected number of units short during lead time. Now when the demand distribution is considered exponential, so what you need to do, that means the probability density function Fx for exponential distribution is given by Fx equals to lambda e to the power minus lambda x. Now this I have written directly, because if you follow the steps to determine the mean or determine sigma L, so ultimately you will get the expression for the mean, that means SL bar equals to 1 upon lambda, and sigma L is also 1 upon lambda. Is it okay? So it's a single parameter distribution, and the mean and the standard deviation are same for exponential the density function. So the expected number of units short NR is given by, we use the same the formulation, that is NR equals to integration from SL bar plus B. B is the safety stock and SL bar is the mean demand during lead time up to infinity, x minus SL bar plus B Fx dx. Now what you do, actually you go for the integration by substitution followed by integration by parts. Okay, so these are all well known the techniques, and with these the techniques by substitution and by parts, So when you integrate this function, ultimately these are the steps just I have mentioned, because the substitution is substituting y equals to x minus SL bar plus b. So corresponding expression comes like this. That means this becomes integration from 0 to infinity, and this is the corresponding expression dy. Then you go for integration by substitutions, and ultimately you get an expression of nr as 1 by lambda into e to the power minus 1 plus t. So what is t? T is the multiplying factor, and if the t is known, obviously the sigma is value of sigma L is already specified. So the t into sigma L will be known. That means the safety stock will be known, and average the demand during lead time, that is already specified, that is SL bar. So SL bar plus B obviously will be your reorder point, that is one of the two parameters of Q systems of inventory control. So here for exponential the density function, demand density functions. So what is the expression for the service level? That is 1 minus e to the power 1 plus t. Is it okay? It is essentially, if you use that expression of SL equals to 1 minus mu into FR. So obviously mu is equals to 1. Mu is nothing but sigma L by SL bar. So for exponential distribution both are same. That's why mu is 1, and FR is 1 say NR by FR is NR by sigma L. So ultimately you get this expression of service level 1 minus e to the power minus 1 plus t, e to the power minus 1 plus t. Now the next important distribution you need to consider in many instances, that is the normal distribution. So if the demand is assumed to be normal, here the density function is the probability distribution fx is 1 upon root over twice by sigma e to the power minus half into x minus mu by sigma whole square into dx. Okay, so this is fx, not dx will come. Okay, so this is just the fx, and then SL bar equals to mu and sigma L is sigma. That means this is the two parameter distribution, and with the probability density function is this one. Is it okay? So fx is this. Now so in this case the expected number of unit short NR is given by, again the same logic we use. That means integration SL bar plus B up to infinity x minus SL bar plus B, and this one is your fx. Is it okay? For normal density function into dx. So if you simplify this expression, ultimately you will find that NR is nothing but sigma into phi t minus t into psi t, where phi t is 1 upon root over twice pi e to the power minus t square by 2, and psi t is essentially the psi t is 1 minus capital Ft, and so the capital Ft is basically the distribution function, and so the psi t is 1 upon root over twice pi integration t to infinity e to the power minus z square by 2 into dz. Is it okay? So if you follow the steps, ultimately you will get this expression. So I am for the time being I am skipping the expression. So obviously the NR, if you want to get an, so the NR for the normal distribution is expressed in terms of phi t and psi t. So the expressions for phi t and psi t already given. Okay, now once the distribution characteristics are known, and for a given distribution, say the demand distribution, when you know the expression for NR, that is the expected number of units short, now our next step will be to develop the total relevant cost equation. Now here what we try to do actually, that we opt for the exact method of analysis. That means what we try to do, that means both the order quantity as well as the the safety stock must be the optimal values of their optimal values must be determined simultaneously. And so obviously you must have a total cost equation in terms of say this both the parameters, the order quantity and the safety stock, and then you follow the usual procedure to get the optimal values of the inventory control or inventory systems parameters, so that the total relevant cost remains at the minimum level. So as I have already pointed out that when you try to design a system, never you assume that the service level the value of service level is 1. Okay, the reason already I have explained. So when you design a system and the service level based system, inventory control systems, so you may assume the service level as 0.9 or 0.95 or 0.99, and so that is your target. So based on this, what you can do, you can also determine the possible the values of the parameters of the given inventory control system. Now if so first thing you have to do at this stage, that is the total cost expression. So if you follow the exact analysis, the total cost E incorporating the concept of service level is given by E equals to, this is the ordering cost to meet the average demand, that means CO into S by Q. You are already familiar with this expression, I don't need to explain it once again. Then the next one is the inventory carrying cost or inventory holding cost for the average demand, that is Q by 2 into CU into I. Okay, so Q by 2 is the average demand in an order cycle, and the next one is B into CU into I, that means this is the carrying cost for the safety stock of amount capital B. And then what you have, that means this safety stock carrying cost for the safety stock is opposed by the out of stock cost. So what is the total out of stock cost? That means per year. So we are formulating the total cost equation per year. So if S is the yearly demand and Q is order quantity, so how many order cycles you have in a particular say year, that is S by Q. What is capital U? Capital U is the shortage cost per unit short. That means we are assuming per unit out of stock cost valid, and this is basically the NR. What is FR? FR equals to NR by sigma L. So obviously sigma L into FR is the expected number of unit short, and for 3 different say demand distributions, so we have already derived 3 different expressions for NR. Okay, so if you have these expressions for NR, obviously you can write down all the 4 components, okay, explicitly in a given of the total cost equation explicitly in a given situation. So after the simplification, this is CO into S by Q plus half Q into CU by 1, CU into I, and I is the inventory carrying cost as a proportion of say the average inventory which you hold. And now the B is replaced with T into sigma L. Cu into I, and this is S by Q U sigma L into Fr. Okay, so all the terms we have explained. Now for the uniform density function, what you try to do, that means here you have the expression for Fr. Okay, so for the uniform the distribution, okay, so obviously you know what is sigma L, and this is expression for Fr. Fr is essentially Nr by sigma L. Nr by sigma L. So this is root 3 minus t whole square divided by 4 root 3 into S by Q. That means for each order cycle, what is the expected number of units short multiplied by the total number of order cycles in a year. So now once the total cost expression is known, taking partial derivative of E with respect to Q and T decision variables, so T is the multiplying factor which is to be used to determine the safety stock, and setting them to 0, we get these two expressions. So this is the partial derivative of E with respect to Q and set it to 0. So you have these expressions. Okay, you just follow the steps, and the second equation you get by taking the partial derivative of E with respect to T and set it equal to 0, and then you have the second expression, and ultimately when these two equations are solved, the simultaneous equations are solved. So the first you get the expression for the Q square, that is equation number 3, and from the equation 2 we get these expressions, in fact, which is referred to as equation number 4. Now substituting the expressions of root 3 minus t from equation 4 in equation 3, I have explained all the steps, we get the optimum values of Q and T as this one. That means the Q star, that is the optimal value of the order quantity, we have used this notation, root over twice S C0 by ICU into these expression, and this expression is 1 minus 2 root 3 sigma L Cu into I by S into U. And what is the optimal say the value of T, that is denoted as T star equals to root 3 minus 2 root 3 Cui by S into U into Q star. Is it okay? So you can derive this expression. Now there are two conditions you have. The first condition is if S into U, S is the yearly demand in physical units and U is basically the out of stock cost per unit, okay, shortage cost per unit short, is substantially greater than 2 root 3 sigma L Cu into I, then the formula Q star tends to Wilson's lot size formula. Okay, and what is that formula? We have already derived it in the previous lecture session. That is root over twice as C0 ICU, and under this condition the classical EOQ the formula you can use, and this classical EOQ is considered to be the optimal order quantity. In the next case, if you find that sigma is very small, that means the variability is very less, we can ignore the contribution or effect of the distribution, and the demand may be assumed to be constant. So maximum value of T is root 3 as S1 equals to sigma SL bar plus root 3 into sigma L. Now what you find that SL bar is equals to, in certain cases SL bar may be equals to sigma L, but here what you do, the maximum value is root 3. That means the sigma L is very less. Okay, so for exponential density function, the total cost expression is almost similar, excepting what you do, that means sigma L is already there, so you get the expressions for Fr. So for this exponential density function, so expression for Fr is e to the power minus 1 plus t. So again you follow the same approach, taking partial derivative of E with respect to Q and T and setting them to 0, we get the two equations like this. This is for after taking the partial derivative with respect to q, and the second one is after you take the partial derivative of E with respect to small t. So ultimately you have these equations, one for the q square, and the second one is for e to the power minus 1 plus t. And once you solve these the two equations, we get the expressions for q, and that is sigma L plus root over sigma L square plus twice S C0 ICU. In other words, it is sigma L plus root over sigma L square plus EOQ. And as for exponential distribution, sigma L is SL bar. So this expression is replaced with SL bar plus root over SL bar square plus twice SCO by ICU. So that means this is the classical EOQ formula. Okay. Now, assuming Q is significantly less than S, now this condition is to be checked. If SL bar is significantly greater than EOQ, then obviously the order quantity will be twice SL, and if SL bar is significantly less than EOQ, that is the classical EOQ, so the order quantity becomes SL bar plus EOQ. Okay, so these are the two expressions we have, and similarly what you can do, that means we have already given the expressions of for NR when the demand distribution is considered to be normal. So the same approach you follow when you assume that the demand to be say normal, demand as normal, or the normal density function you assume, and the same approach you follow and to determine the optimal values of order quantity and the safety stock. And my suggestion is that you try to extend this approach for the P systems of inventory control. So obviously, while you formulate the total cost expressions for the P systems of inventory control, so the total cost expression must be the derived in terms of the order period and the safety stock. Okay, so the later on we'll refer to such cost expressions. Okay, so thank you.